you try to see the right now.
Like the job explained to me, I'm also curious in the field. Younger than you, put you more less pressure, so like no problem. We've seen more shyer than you, I guess.
Okay.
So I'll put just the light on. Okay. So the mic is on. I just bring the setup.
Yeah, okay.
Signal.
Okay. Okay. Today I'm going to present my work is related with vision transformer, especially the way that we are going to perform multimodal brain tumor segmentation. And the idea is try to evaluate different kinds of architecture using transformer. In the first one, we want to see what is going on if we perform with the different modality. We perform an early concatenation, and after that we apply, in the lattice space, we apply the transformer. Also, we try to separate the different modalities. With the different modalities, we are putting, after that, in the transformer, we are going to perform a fusion after that. And the other one is to use a plane transformer. That is the traditional one. For the fusion part, actually, we are use 3 different kinds of transformer. In the first one, we have a single string transformer. The idea of this kind of fusion comes from the natural language processing. The idea is to add, for this one, the idea is to add an additional token information that gives you the information of a learnable token that gives you the information of the different modality. This one is the first one, and the other one is try to perform self-attention, and after that, cross-attention. In the implementation detail, we use, like for typical medical image segmentation, we use all the pre-processing coming from the NNA unit. And also the dataset that we are going to use is BRAD dataset. That is a dataset that is composed of 1,251 MRI image, multiparametric MRI image that are composed of FLAIR, T1, T2, and T1 Gado. And at the end, we can find out that actually the hybrid transformer, that is the transformer that is combining CNN and transformer, perform much better than a plain transformer. And the conclusion about this is that by the moment we need to take advantage of the hybrid method and try to give the transformer some local information to improve the actual performance. And also we see that for the case that we use different kind of fusion strategies, doesn't help to improve the model performance segmentation at the end. Thank you. ¿Se bien?
It was really good.
Okay. I am not that sure.
Yeah.
you have to do it? I'm quite confident if you No. Okay. No, because I'm no, because it's just that the camera. I'm not very
you don't
very easy.
You explain to him.
Yeah. Thank you. I have a brain, you know. He knows I can just. So I don't know how long is 3 minutes. Oh, sorry.
If it's small, no problem.
Okay.
I just.
Okay. Hello, I'm Yekta Kesenji. I work at Institut Pasteur. This is a collaborative work with my friend Alesh in EPFL. So we work basically on quantifying the dynamic behaviors of cells, and here in the special instances of cancer cells during migration. So biologists have different tools to quantify the different values of the stiffnesses or the viscosity of the cells, but they quite fall short when they have to quantitatively evaluate some of the dynamical values of these cells when they are moving in real-life situations. This is a problem, but this can be counteracted with the use of imaging methods, and here we propose one. So, giving the nucleus of a cancer cell here, a glioblastoma cell, that is moving through the tissue to invade it. We try to use its ruling behavior, taking into account the different properties of both the lamine and the chromatin, which are the main constituents mechanically wise. And we combine it with an optical flow technique in order to try to estimate best the displacements, deformation tensors, and the stress tensors, as well as the interactions on the boundaries. So this works as a two-step method. The first step uses simply the optical flow techniques with the images of the deformation to get a first estimate of the displacements. And then the second step, use these displacements to project it to the kernel of the linearly elastic equations of the cell. And to evaluate the accuracy of this method, we tried to do some numerical computations. We took an image of a glioblastoma cells. We used the finite element method to warp it with the different values of traction and different values of compressibilities. And all this warping landed us a bank of images that we could use then to evaluate our method. So when we compare this method to other well-known image registration techniques, we not only see that our method is consistently better, but also it is consistently more stable. One of the also advantages is that, well, while the other techniques are also quite accurate in computing the deformation and the stress, they really fall short about the traction on the boundary, and this is a particular value of the biologist. And here our method offers here a compelling alternative. No. You're too nice.
Moi je savais qu'il allait passer. Attention, merde, c'est éternité ça. Des milliers de personnes, des gens en live.
Sorry for the interruption. If you have any question, I can. Do you mind if I just take a copy?
One single question. Sorry. Yeah. Sorry. Just one second. Oh, sorry. Can I answer him or? If you can, just so we can. Okay.
Working good. So this paper is a paper, smart learning of click and refine nuclei for nuclei segmentation on histology images. So we are working on histology images, which are WSI. And this kind of images are quite big. They can weigh up to 2.5 gigabits when they are compressed. So this image is in terms of pixel is 200,000 pixels times 100,000 pixels, so real big. And what we are doing here is nuclei segmentation. So nuclei segmentation is very important because it gives you a lot of information about your patient. Because some criteria such as the area ratio between the cytoplasm and the nuclei, the shape of the nuclei, the size of the nuclei, their density, gives you some insights about, let's say, if there are tumor areas or metastases, etc. So there's already a lot of methods that do nuclei segmentation, and what we want to do is to have a method that will be interactive and that will correct this segmentation. So the pathologists will click on regions where the segmentation may have failed. Let's say a patch P where this segmentation may have failed. And the thing is, he cannot click anywhere on the tissue where the segmentation has failed. So we're gonna retrieve all the patches PQ that look like this patch P. And then we assume that if the segmentation failed on patch P, then it may have failed on patch PQ, according to the distance. So the thing is, we clicked on this patch, but we didn't click on that one. So we have to generate a click on the patches that look like P. So the idea is just to train a neural network to infer a click map. So it's very easy. To build our dataset, you take a patch, an initial segmentation, and you compare it to the ground truth. If some nuclei matches together, you do nothing, and if it doesn't match together, then you generate a Gaussian, which will be a click. So thanks to this, the dataset we defined, we're gonna have our patch here, the patch where we clicked on, and a candidate patch. Then we're going to be able to here have a Siamese network to compare these two patches and infer the distance D. If the distance is under a certain threshold, then these two patches look alike. But on the patch that we didn't click on, we're going to infer our click map and predict the false positive click map and the false negative click map. We add them together to get the click map. And if the distance is below a certain threshold, then we have to refine the segmentation. So we're going to pass it through the second neural network that will correct the segmentation. So we have our patch, we have our click map that will act as an attention map because it's the regions where it should have failed. And so there's an encoder here, and we're doing the product as an attention map. And here, as a decoder, we'll use the activation function, Tanash activation function, to either erase a nuclei, so -1 if we want to erase a nuclei, and +1 if we want to write a nuclei. And we just add them to the initial segmentation to get the new segmentation. So this is our results of our predicted distance. So you have here a patch, candidate patch, here and here the most similar patches. So you can see it's quite similar. And here are some results. So we took 3 baseline segmentations, overnet, Masker-CNN, and Stardist. So you have the baseline segmentation here. This is our model, and this is the ground truth. When you see the white squares are the regions where the baseline segmentation failed. So you can see that it performed well on, let's say here, writing this nuclei. You can see it's on the ground truth. Erasing that one, it's not in the ground truth, and it was written by the baseline segmentation. And you can see that Stardust and Overnet are performing quite well, but Mask-RCNN is not doing that great. So on the result, you can see that here, Mask-RCNN, we are improving a lot. With any of the metrics, there's a lot of improvements, but with Overnet and Stardust, we're still improving, but not as much as Mask-RCNN, but it's a bit comprehensive, I guess. No problem.
Okay, good. Hi everyone, it's my pleasure to present our research work entitled Non-Deterministic Face Mask Remover based on 3D Prowl. This is a joint work by my former PhD student in Xiamen, Professor Huang Di from Beihang University, and myself at École Centrale de Lyon. The aim of this work is to remove face mask on face images so that downstream applications could be more efficient. How can we do that? Because it's not easy to remove a face mask, and behind the face mask, one person could have different facial expressions. That's why our work is non-deterministic face mask remover. The work is composed of two parts. The first one is to predict the mask position on a face image, and also the face pose using a 3D morphable model. And once we have the mask position, the the synthesized image with the pose information and facial expression information. We put all this together into an imprinting module, which synthesizes the face image with the true texture from the original face images. And we have also adversary training, making use of a discriminator. So basically, compared to the original image and synthesized image, this discriminator tries to distinguish from the original image the synthesized image. So the difficult part is to generate labeled face images with mask. What we have done is we take input face image, and we have a set of different masks with different textures. We generate a face image with mask online, and so that we, when we train the mask segmentation image, we have the ground truth on the mask position, because the mask is added artificially in this training process. What is important is this part. We are predicting the parameters of a 3D morphable model. These parameters with different attributes and numbers to change facial expressions of the synthesized face images. Thank you.
I agree with you. I think this is a debatable. I'm not sure if this one is much better than the one here. Experimentally, we find more or less the same values. Oui, alors moi c'est Pasteur et puis and then you only present the high pass. Whereas here we don't need this
Thank you very much. 写真撮ったり。あ、いいですか。やらないことにしましょう。あんまりことない。気持ち悪い。海外用語したくてしてるので、成果はあんまり別に話したくはない。最初のお金で、そう最初のお金でやったわ。But you know, this is
So what should I do?
Just a presentation of the work you can zoom and also with our writing.
Just show what did I do?
Present your work how you see it, how the experiences and
How long should I Okay, I didn't do anything for the... So, right now? Okay, my work is to analyze how human behavior changes in the distortion video. So from the first one, it's we calculate the entropy from the saliency map, and we use this one to classify the two groups from this database. And this database it includes 116 videos, and we use 116 humans to do this eye tracker experiment. And in this video, in this database, there are 10 reference videos and 150 distorted videos. So we want to find out what difference between the human behavior change in the high-level videos and low-level quality videos. So this is the conclusion is from the content. We use the entropy to classify this video database from the two groups. The first group is from the RH to the PA, and another one is from the PR to the ICIP. That we said that from the RH to the PA is a multi-object video content. That means there are a lot of objects in these videos, and the entropy is very high. That means the sentiment map is very random. And another one is from the research on the time order. The time order shows from the time block, because this video has 10 seconds in one video, so we want to find how human behavior changes in the time order. So we can find that in the beginning of the video, the correlation is very high between the reference video size map and the distorted video size map, and this means that maybe it's because of the central bias. But in the middle of the video, so people pay more attention on the distortion, so the correlation is very low. So we want to get a new weighting function on the video quality assessment. So this is my next work to how to get the new video quality assessment models.
And that's all my presentation. Is that finished?
Yeah, you can do your job. I just need the pockets. Well, you can watch me online.
Okay, merci Osama.
There you are, please. How much time do we have? 3 minutes? Okay. You will be next. Okay, good. Hi everyone there, virtual poster, if you can say. My name is Oussama Missai, and I'm from University of Lyon in France. So here is the objective of my work is to propose a model that can assess the quality of the image. It's just a model that give it the image, and it gives me back the quality of the image, whether it's bad or good. Okay. So here, what's the main contribution of our model is this: is like we propose a new concept based on multi-score predictions. Like instead of giving one score, we give multiple scores. A score for the left view, score for the right view, a score for the stereo view, and the global score. So it's multiple predictions and multi-input and multi-output. It's a multitask model. And the other thing is it gives us also quality maps as the final. And everything is end-to-end. So we don't need pre-processing. We don't need to change the size of the image. We don't need anything. We just give it the image as it is. As for any resolution, it can work. So as long as the resolution is bigger than 32 by 32 size. So this is the main contributions of our model. And then here we demonstrate that if you suggest, instead of doing all of this, compute score for the left and score for the right, and do simply calculate the average. And here we demonstrate that if we do this, we will be always having a mismatch between the average and the stereo score, because the stereo score, people were wearing like some sort of glasses to see the 3D scene. So they give us a score for the 3D scene, not for the 2D scene. So this also we have 10% improvement compared to the latest state-of-the-art metrics. So here we can see the results of our approach, and you can even try our model here online. You just tap this website and you can try our model online. You just give it an image and it gives you back the scores and the quality scores. Here, green is bad quality, green is good quality, and red is bad quality. So yes, and there's also code implementation code is made available for you to download and just try this. Yeah, I can give you back. Okay. Thank you very much.
You're welcome. It is really a correlation. Thanks.
Okay.
Okay.
Start. Hello everyone, my name is Deng Si and I come from University of Sparse, and this is my poster. Our work is focused on the no-reference measure for uneven illumination assessment on the laparoscopic image. And to do that, this is our proposed method because we want to focus on the lighting effect of the light source. That's why we want to extract the background illuminance of images. For the first time, we want to convert the image from the ICIP color space into the XFE color space. What is the reason? The reason why we want to get the V channel, this is the independent the channel inside the color space, and then we got the illuminant component feature from the V channel. And then to get the background illuminance, I get the low pass filter. The low pass filter because we want to get the background features, and the background feature is a low frequency. Because we want to get the low frequency, I got a low pass filter with the last side of kernel. It's very simple kernel with the it's the 1/4 of the side of the images, and then I got the background illuminant like this, and then we want to illuminate. I want to access the effect, the histogram equalization mapping effect into the background illuminance. That's why I apply to the histogram equalization into the background illuminance of the images. The histogram equalization effect is increasing the contrast because it will be brighter. It will be the bright region will be brighter and the dark region will be darker. That's the reason why I got the higher contrast image like this, and then I got the subtraction between the background illuminance and the equalized image to get the result like this. Okay, and I got the result. We have a tensor right here. If the image have a good quality, we will have the lower gradient of the subtraction. If we have the worst quality, we will have the higher gradient. From this observation, I can calculate the standard deviation of the distribution of the subtraction to get the index like as uneven illumination assessment. To evaluate it, we can evaluate into the data set with the substitute score. What is the substitute score? The substitute score is the score from the doctor evaluate the video by 4 levels from the worst quality to the best quality. We have 4 levels and we calculate the correlation, the score from our equation to the doctor score to get the correlation. We have 2 kinds of correlation here. It's the speed range ordinary correlation coefficient and the Pearson correlation coefficient. We have the better correlation, we have the better performance, and we have the similar performance to the doctor. That's why in this table we can see here our performance have the outperformance no reference matrix and competitive performance to the full reference images. We have a tension right here. In the medical aspect, we don't have the reference images. That's why the no reference matrix we will have a potential compared to the full reference matrix. And this is the first part. The second part is, for example, I have a paper, I have the white paper, and I have a black paper. I have the same gradient, but the different quality. That means we should consider all the value inside the graph to make sure that our model can predict all of every level of distortion inside of the uneven illumination. That's why we have plot the scatter between our score with the expert mean objective score and the non-expert mean objective score. We got the logistic function like this. If we have the logistic function, that means our model can predict all the value inside hit the similar real life. That means we have model have the same performance with the doctor, with the performance in the real life, and can apply into every expert of the images. And in conclusion, we have proposed a method have the similar performance to the data. We have a good performance compared to other no-reference metrics, and we have metrics can be applied into the real-life recounters. This is our result. Thank you for watching. Okay.
Thank you. Thank you. You're welcome.
Hello. It's online. You can finish work in a few minutes or more or less. No problem. No, I can because many forget. Isn't yourself on university?
Yeah, I will.
Sorry. Yeah, can you please hold this back for me? Okay, sure. Thank you. Hello, I am Professor Jayanto Mukhopadhyay from the Department of Computer Science and Engineering, IIT Kharagpur. So I am presenting the work that is on lighter and faster two-pathway CMR net for video saliency prediction, and the work is primarily done by my PhD student Sai Fani Kumar Maladi, and also I have collaborated with Professor Mohammad Shekhar Larabi of University of Poitiers, France, and Professor Shantanu Chaudhary of Indian Institute of Technology, Jodhpur. So in this particular work, the primary concern was to develop a saliency model for the videos using a lighter model. What happens that usually the saliency model which are computed using deep learning based technique, they use the features extracted by existing standard feature extraction network like VGG and other kind of network, but that makes the architecture heavy, and that there are large number of parameters in those architectures. To circumvent that, so what we do that we have proposed a de novo architecture starting from the very scratch, and that we did for the image saliency in our previous work. In the previous ICIP we reported, and which we called as a concatenated multi-resolution block, and there you can see that there are features are computed at 2 resolutions, and they are fused, and it goes in stages, and finally those are used for predicting the saliency. So we call it as CMR blocks. We extended this work for computing the video saliency, where we have considered also the temporal information of the video, not only the frame-wise computation of saliency, but also the optical flow we have used for the temporal information, and a sequence of optical flow frames, they are processed. From there the features are fused, and then there are attention blocks by which we took the relevant features from there, and that goes to the finally goes to the prediction model. There is a bidirectional LSTM which learns also two-way information flow, and by which finally you can predict the saliency model. So here are some of the results, frame-wise results you can see, and with respect to the ground truth, you can see that different kinds of saliency computations, and the last one is ours, and this is the ground truth. This is the first one is the ground truth, and these are different techniques, and we can see that our result is very close to the ground truth. Of course, there is another network which is also the best performance. What we find also in our comparison table, they are called extranet, and they have higher figures, but ours are also very close figures, you can say from the metric point of view. But if you see the number of parameters in our case is a list. A very a drastic reduction. It is only 4.9 million number of parameters, whereas the best model from quality-wise, STRA-net, it has 46 million parameters. But other networks has much more larger. So in that way, this network we expect that this could be used in various cases, because nowadays this video high definition videos are more and more are going to be used, and for that saliency computations is required for their for processing them to get the relevant zones. So that is how our method would be very useful for them. Thank you very much. So was it okay time-wise?
Yeah, it was really good.
Okay.
Yeah, so it's point by point.
Oh, thank you very much. Thank you very much. Okay.
Point by point.
We had to wait for like 10 seconds. Yes, I can try. Yeah, I mean, I explained it a few times before, but yeah. Il n'y a pas de souci.
Oh, ok. C'est vrai quand on est français, en fait ça peut... Hello, I'm Christophe Kobe, and we are presenting a paper called the Case Study of a Calibration Problem in Acquired Hyperspectral Images. So for those who might not know, a hyperspectral image is an image in which instead of having the three usual color channels R, G, and B, you have like 100 or 200 color channels. However, in this kind of imaging, there is very few data available publicly. So we wanted to acquire our own data set of surveillance materials acquired under varying illumination conditions. We acquired such a data set with around 40 samples acquired in 6 different illumination conditions, mostly indoors, but also one session with sunlight illumination. Our main goal using this data is material classification by comparing the reflectance and the raw data. So we first computed the calibrated reflectance data by calibrating the images. However, in the produced reflectance images, we saw that some negative values appeared. Negative values mean negative illumination, which should not be physically possible. We analyzed the dark current images used for the calculation of the radiance, and saw that the values increase over time. This is actually a major problem because we do not have a dark current image for each sample in time. We also conducted further analysis on the dark current images, and we saw that indeed the values of the dark current images increase over time, but also over time they seem to evolve to a saturation point. It is actually probably due to the heat of the halogen lamp used in the acquisitions, which in turn heated the camera, which resulted in increasing values over time. We wish to fix this problem. So in this case, we have two main cases. In one case, we have negative values appearing in the images, which, as we told earlier, was not possible. However, in some cases, using a dark current image, we produce images that are not properly calibrated to radians because some of the noise of the sensor still remains in the images. So we tested multiple methods and find out that using an interpolation between multiple dark current images produces the best compromise because it leaves the minimal amount of negative values while removing most of the noise of the sensor.
Non, non, je n'ai pas. Je suis fatigué. J'ai même pas mangé. Merci à toi. Your supervisors, but sure. Because I definitely forget and
when you read the paper,
Right? It's video recorded for all of the presenters.
So my question is, now I'm working with trying to
oh, okay.
Yes.
Yeah.
So I'm trying to find another way when you're ready to say that.
Yes, of course. Definitely.
Number works or which one? Number or email?
Email, I think, if you can. Or you can send a message, but I will not be able to check on my phone as well. Yeah, actually, I made this like last week. Yeah. But I think it's my first conference, so I wanted to have something to. Your supervisors are both at one, so I think they can progress you.
When you present the paper,
In the case of 8-bit data, 32-bit data, quite simple. The tree becomes much deeper and there's much more information needs to be simply because the levels in 8-bit, the longest path you can have from leaf to root is 2555. In 32 bits, it can be the whole thing. So you have far more. In many cases, you don't see much speed up in the case of floating point. Actually, if you do it in parallel or distributed, but at least you can compute it. Can I? Yep. Wire me up.
Okay. Oh well, here. Okay.
sound is...
Okay, I'll try not to overload the mic. Yep. Okay. All right. So, yeah, this is our work on parallel distributed computation for distributed component forests. It's work by Simon Gazagne, a former PhD student of mine who's now a postdoc at the University of Texas at Austin, who unfortunately couldn't be here. He's in the Department of Astronomy. I'm of the Bernoulli Institute of Mathematics, Computing Science and Artificial Intelligence. So, of University of Groningen. Anyway, so the context here is that we're trying to parallelize the computation of attributes in so-called component trees. Now, a component tree is a tool that is used for computation of connected components that are nested within each other. So you can threshold a grayscale image at all possible levels and then compute connected components in each of those binary images. And these are nested within each other because at a higher level it must always be nested in just one component at a lower level. If you do it like that, it's going to take forever. But there are plenty of fast algorithms. The first one was provided by Philippe Salambier in 1998. And there's been a lot of development in faster algorithms, and in particular parallel algorithms. Now, a tree by itself is not that interesting. What is important is that each of these nodes can get an attribute, a property, a feature, if you like, or even a feature vector. These are usually, specifically in the parallel algorithms, computed during the building of the tree. A simple example in 2D would be the area, but you could also have, say, elongation, you can have shape measures in there, orientation measures, it doesn't matter. However, you sometimes decide, in hindsight, that this was perhaps not the best attribute to compute, so you want to compute something else. Now, that can be done sequentially. It's much more difficult to do that in parallel, and this provides the first attempt at doing so. So the idea was borrowed from a distributed memory algorithm in which you don't compute one tree, but you compute a forest of trees, each for a tile of the image. And once you've done that, you communicate with each other with boundary trees, which are basically the subsets of each of the tree that hit the boundary of the tile. And this allows you to update the structure of the tree, the topology, and the attributes, the features. Once you've done that, you can filter each of these separate trees, and you get the same result as if you'd filtered this one huge tree that you can't store in memory. Now, the idea is that you can not just use this for computing trees with attributes, but maybe you could also say, I don't have to rebuild the entire tree, I can just compute the attributes and use the boundary trees to, again, communicate to the neighbors how they need to correct their attributes. If we do that, we see that for 8-bit per pixel data, we get a clear speedup, which is shown here as a factor of 2 on average. So it's not a huge speedup, but still a factor of 2 gain, and what are complicated computations helps. In the case of floating point data, you have longer branches in the tree, if you like, that you have to communicate with your neighbors, and then you only get a 50% speed gain. But still, this is the first time that we have been able to compute new attributes in component trees, or in this case forests, in a parallel manner. And we hope to apply this to very large astronomical data sets and also remote sensing and many other applications. So, that was it. Thank you very much.
Shy guy. What is the average? You know, the average success that you have? So many people want to do it, or you are one kind of people over how many? I'm talking about the people, but the people who actually want to record the movie. Most of the
So the experiment showed where also on the scenario
okay, you have some computational power that much. Even running this stuff like different files and cardinality.
D'accord. Est-ce qu'on fait tout ça sur Discord?
Yeah, to point things.
So, yeah. I might stop by later.
You can
stay next to me. We already were in a relatively deep discussion, which I don't think that.
You know, if you sing
about the
whole thing, you know, if you want, I can point to this paper. It was in ICIP, you know, before the COVID pandemic. That we present this
in La Coruña?
In La Coruña, yes.
I was there also.
Yeah. Okay.
That was exactly before the pandemic.
Yeah, before the COVID, yes.
Okay. Get ready.
Oh, okay. Hi, my name is Paul Rodriguez. I am from Pontificia Universidad Católica del Perú, and I am presenting this paper, Random Generated Dictionaries for Convolutional Sparse Coding and ELM Interpretation for Simple CSC or Convolutional Sparse Coding application. So what is the main idea? ELM, or String Learning Machines, is just a name for a particular architecture of convolutional neural network in which they use random filters. So there is this interpretation that the layers of a neural network can be understood as a dictionary. So when I was reading about this paper, which is like 20 years old, I was thinking, what if we use a random dictionary in other instances in which learning those dictionaries takes a lot of time? And since I was working on convolutional sparse coding, I decided to try what happens if we use convolutional filter bank in order to represent the data. Basically, the main result of this exploratory paper is that when you use a random dictionary, you get, for representation, you get better performance than when you use a learned dictionary. Definitely, there is something deeper going on here. Right now, I don't have the full explanation. As I mentioned at the beginning, this was an exploratory paper, and I hope to keep working on this topic. Thank you.
Identification.
Yes. I can do
Okay.
Perfect. Thank you very much.
We have track rates. Yeah, tracks. Yes. And we have ID. And current frame. In the current frame, we have
some of the detection results. And we have identify which detection. Yeah.
Let me see whether my company allow or not.
So the mic is on, is already here.
Oh, okay. Okay, so basically in this paper we are trying to present MANet, trying to do the micro-annulus point checking in the cardiomagnetic resonance. So basically the overall architecture of our network is shown here, right? Basically have two main parts. The first part is for the point checking. We are trying using the CAN connect to the fully connected layers, trying to detect the 2 points, or as you can see the 2 points for this 2 chamber, 3 chamber, 4 chambers. After we detect these 2 points, then we can, according to the 2-point coordinate, trying to extract small regions from the MR images. Then within this small region, we are trying using the Kalman filter to refine the points. In such a way, we can get a better, more accurate position of these 2 points. After that, we can, if we get the 2 points position in each of the frame, we can get the motion track of these points. Then you get some of the index, like the displacement and that's the motion velocity. These 2 index will be help the doctor doing the cardiac function analysis. So our AI solution can help the doctor eventually can help the doctor doing the cardiac function analysis and the diagnosis. So this is all we've done. Whether
Thank you very much.
Oh, it's done. Sorry, sir. Without so no.
Des trucs médicaux, les gens, il n'y a pas une connexion de
Il faut qu'on se déplace. C'est pas notre tête, nous on est là. C'est Charles. Charles.
Alors, c'est
Donc bonjour, je m'appelle Charles Dormeval, je viens de l'université de...
Si possible en anglais.
En anglais, oui, pardon. So hello, I'm Charles Dormeval from University of Nantes. We're working on a problematic which is when is the cleaning of subjective data relevant to train UGC video quality metrics. So we are in a context where, for example, on YouTube, people are exporting videos, and the quality of the video will really change the encoding recipe, the encoding part. So, for example, if a video is of bad quality, we'll have to apply a different encoding step from a video which is really of good quality. So this part of quality assessment is really important for the rest of the pipeline. So we are working on UGC content, so it's user-generated content. So it's UGC video quality metrics. So we work on no reference because people are uploading what they are filming, so we have no reference. Quality metrics are more and more driven by data because it's machine learning, deep learning, so we need a lot of data. And to do so, we have to use crowdsourcing, and there is an additional challenge because with crowdsourcing we can control really the environment, how people are doing the subjective tests, and so we have to screen to reject those people because it will affect the way our quality metric is gonna learn to assess quality scores. So we did a data cleaning part with two algorithms that are MLSEO, which is more and more used in the domain, and also with GPM, which is a probabilistic model. And what we're doing is to screen people with their bias, which means how expert or not they are, because we want scores that are representative of the global population, and also we want to reject people that are assessing score randomly. So we did this cleaning part and found out that on YouTube UGC H264 there was 11% outlier, and what we are interested in is what is the impact of training of outlier noise on the training of UGC video quality assessment, UGC video quality metrics, sorry. So we did a benchmark to represent this difference with all the data from YouTube UGC, with and without outliers, and we found out there was not so much difference because YouTube UGC only have 11% outliers, so it's quite lean for crowdsourcing. And so we did a third part for this study, which is increasing this percentage of outlier to find out what is the impact of more and more outlier percentage in the data. And the conclusion is quite expected because the more outlier you have, the more noise you will have, and the more you need to apply outlier screening. So at first it's transparent because we could think removing data from the data set will give we will lose in accuracy, but it's not the fact, it's not what we found out. Removing outliers will have at worst no effect at all, and at best you will really increase your performance. And the last thing is that the pipeline we constructed allow to measure how much quality metrics are robust to outliers. Because sometimes datasets only provide mean opinion scores, which is the aggregated ratings, and they don't provide raw scores. So you have to trust them in this mean opinion score. And the fact, and knowing that your metric is robust to outliers, is a great advantage because you can train safely on this kind of data sets. So that's the main goal of this study. Yes.
Just 3 minutes. 3 minutes.
More or less, no problem. More or less.
Okay. So here we present learning graph features for color mesh quality, visual quality assessment. The novelty of our work is that using first color, to extract some information from 3D image, and with combining with some geometrical attributes, we can predict the quality. First we construct a graph, a weighted graph, and weights are based on color information to be computed, and so we use some topological properties that we can extract from the graphs, and for each vector of topological, like a degree, centrality, clustering coefficients, we can compute some statistical measures like mean, variance, skewness, kurtosis, and entropy, and we construct a signature vector that will be fed to the random forest regression. We have compared our methods with an ablation study without weighting in the graph and without RGB, with RGB color space, and we remark here that our results are performed comparing with the RGB color space, and also we have compared with the state-of-the-art methods, and here we can see that we surpasses some methods like method based on natural science statistics. Thank you for your attention. C'est bon?
Merci. More or less, no problem. 3 minutes. More, no problem. Less, no problem.
We did today my session because
no, he is the presenter.
well, he's not co-author. He was asking. Okay, now, because I have to leave.
Okay. So I have to leave me too, but do I have to stay like this? Or? Okay. Why you come
just to make it like a scenario.
Yeah, okay. So,
you can proceed. No, because I have to. Because I have the post.
You can do it now?
Yeah, no.
Okay. Ok, donc on discute demain.
Ok. L'après-midi.
The mic is on.
Okay, this is my poster about new video quality assessment dataset for video surveillance application. So the motivation is that we know that for high-level tasks may be affected by the quality of the acquired videos. For example, noise, uneven illumination, low illumination, all these kind of distortion may affect the performance of high-level tasks like object detection, abnormal event detection, and the classification. So what we did, we developed this data set that has been used also for a challenge session that I have presented yesterday morning. And we start from 36 videos representing different scenarios, like in the parking, in the stadium, street, highway, and so on. And what was the objective is, so we generated by computer different distortions like noise, uneven illumination, at 4 levels of severity, but we have also generated different mixture like containing, for example, 2 different distortions, but also 3 different distortions. So the challenge was to ask these competitors to propose solutions to identify, classify the different distortions, identify each distortion, single distortions, and the level of severity. The second level of difficulty is to detect identify the mixture, the ingredient of each mixture of the distortions. And the third high level of difficulty is given a mixture to detect the ingredient, not only the ingredient, but also the level of severity. So here are the graph showing the diversity in terms of structural information, color information, spatio-temporal information, to prove that this data set is really rich and there is some diversity. So this data set could be used not only for video quality assessment, but also to benchmark different algorithms like object detection, visual tracking, and abnormal event detection and classification. So this data set could be downloaded from this link, and we have also paper associated to this poster where you can find all the details and the information about this data set. This is what I can say about this poster, and you can find all the details on the paper. Thank you. But I don't know if the sound was... Thank you very much.
Actually, we hear it because of it. It's microphone that is done for this type of it is like the way this communication is more closer with what is the products product is Thank you very much.
If you met the
Thank you very much. You are with the no, there is a company that is doing all the online, but for me, I am a student. This is a club of the engineering school of ICIP here in Bordeaux. Okay. And we are students, so we're doing this. So we come with this solution. We've never seen before, like to do a live thing. And so we. Can I take a picture of you guys? Okay. Thank you very much. What was your name? My name is Anas. Anas. So if you are in university professor in also in Singapore, Singapore has a course. So you have a course. I even didn't know that you were somebody. No, il est moins calme. You find the mic is already on.
Okay. This we can put here. No,
then I stop because
all right.
Okay. So I'm António Pinheiro from University of Beira Interior in Portugal, and we are working with quality evaluation, and in this work particularly we are working with quality evaluation of holograms when they are coded with codecs, regular codecs. So most of you probably don't know about holograms, but they are acquired creating interference patterns with a setup like this that we have here. So the light goes into different paths, and that will create some interference patterns that are detected with a camera, and they are like this. So we don't see anything here, but we can easily create this kind of representation that is the hologram plane, and after that, with some reconstruction, we can see the hologram in a regular display. So what we are thinking here is that we need to compress these holograms because usually they are huge, and we collaborated with JPEG, a project called JPEG Pleno, to compress these holograms, and for that we need to create some quality evaluation protocols. So this was our earlier study on these protocols. It is presented on a journal paper in IEEE Transactions on Multimedia, and we took it here to show the importance and the models to everybody here in the ICIP conference. If you want, I can go with deeper details, but it's okay. No, for me it's okay. Okay, let's go with more. So do you want to do more?
If you want, yeah.
Okay. So our initial study only considered the holograms reconstructed in the frontal view position. And we could see that there are optical holograms that are created with a setup. There are holograms that are created with computers. Usually most of the holograms that we speak about, we see on TV, and all these things are created like this. And they have different natures, so the quality protocols must be adapted to each one. But at some point, holograms are 3D, so we need to find a way to
evaluate them, their quality, based on the 3D information. So what we did is, instead of reconstructing them in the original position, we start reconstructing them, viewing them from different positions. So we have a hologram, we look for them in different positions, we create a video with these qualities, and then we evaluate all the video. So with this way we could see the hologram in different positions, so we have 3D information associated to this. And the quality is quite different when we see it in this way. So we understood that we cannot rely on this kind of evaluation of simple looking to the hologram. We need to see what is going on the 3D information. And this is the major thing in our work. Okay, thank you.
Thank you very much. It was good. Thank you. The mic is already on.
Oh, yeah.
Yeah, okay, so you're working on that. Yes, yes.
Thank you.
Hello everyone, I'm Saeed Mahmoudpour, a senior researcher with the Department of Electronics and Informatics at University of Brussels and EMEC. And I want to present my paper entitled Omnidirectional Video Quality Index Accounting for Judder. So the aim of this paper is to evaluate the quality degradation impact of Judder in head-mounted displays. And what is Judder? So the Judder is a motion-related artifact that happens when you are tracking an object on the display. So we have like a space-time diagram here, which shows that in real-world object tracking, the location of the object to the eye is not changing. But when you have a digital display, the location of the object during the object tracking can slip over the retina for the duration of the reference time, and this can make a kind of choppy motion blur when you are tracking the object. So we are somehow simulate this choppy motion blur here that you can see, but this happens when you really track the object. And the idea is just we want to know what is the degradation impact of this Judder when the user is actually using the omnidirectional videos. So we made a subjective experiment for that. We made our own videos because the videos should include an object in it, which is going through a trajectory in different speeds. We have like 15 video sequences at 3 bit rates because we are also interested to know what is the impact of compression together with Judder. So in total we have 60 videos, 45 process and 50 reference ones. And we did 2 tests. So the first test is about just examining the picture quality, means that just the compression quality. So the people can just look around the video and give the score. And the other test is really about to know that what is the impact of Judder, where the subjects will track the object in the scene. And we have 2 scores, the CMOS, which is the compression MOS or picture quality, and the OMOS, which is the overall MOS. Here you can see the plot that shows the CMOS versus OMOS. As we can, so one interesting observation here is that at high picture quality, means when there is no blocking artifacts, compression artifacts, the impact of Judder is very significant. You can see the quality drop for high speed, like this is the medium speed, the red circles are medium speed videos and the triangles are like a high speed videos. So you can see a drop of the quality there. And yeah, And we also have the visual masking effect, which can somehow cancel out the Judder in some videos. So based on this observation, actually, we also developed a Judder quality index can account for visual masking and the Judder impact together, which can be plugged into any objective metric to make that objective metric account for the Judder. So our experimental results shows that when we are using this Judder quality index in the objective metrics, we have an improvement in the correlations to the subjective scores in our data set. Our data set is publicly available and accessible for the scientific studies. Yeah, thank you very much. Okay, it's quick. It was not that long.
It was good, yeah. Perfect. Thank you very much. So just to
Like the experience that did you stop?
Experience as long as the edges, the degree is relative low. So I just now the issue.
So you can restart from the.
All the way here. Then you might need a lot of time. That part. Yeah. But basically, I don't have to wake up. Actually, I like this.
It's live session, right? Okay. So, hi everyone. I'm Isidore Dubuisson from a laboratory from Saint-Étienne, France. My work is about color constancy. Color constancy is the ability to be robust about the way we see objects under varying illumination conditions. The classical approach is just to predict a gray patch in an image and apply a diagonal matrix to the image to color over the different RGB channel. But there is a limitation about that. We have here two different light sources with different spectral distribution and a camera that captures a color checker. And we just project all those patches in a red-green chromaticity space. And we can see that the gray patch under the different light sources are same, but not, for example, the patch 50, which is the red, which appear clearly different under the different light source. So the idea is to use more information than the gray patch to correct the image. Here is our process. So you can imagine we have an image. We try to predict how the color checker would be in the image if it had been in the scene. And from the prediction we can get from the CNN regressor, we can calculate the optimal matrix transform to go from the wrong color space to the white balanced color space. And we can simply, at the end, apply our transform to the input image to get the white balanced image.
Thank you very much.
For example, this is a case of partition. So each block of pixel is partition more or less
Les vidéos, les cours, les vidéos.
Moi-même, en fait, j'ai pas les mêmes, en fait, j'ai monté par ce là. Vous pouvez le voir maintenant, par exemple,
Ah non, mais c'est en direct, attention.
Oui, mais c'est en direct.
C'est toi là, non? C'est ça. C'est 2022, c'est ceci.
On a deux formes de lumière blanche.
Mais après, il n'y a pas de seulement deux causes.
Mais en fait, le vous savez pas que c'est un intéressant, mais on va regarder les différents patchs. Du coup, ça marche plus. On va aussi attendre les patchs sur les patchs. Par contre, les patchs un peu plus sur le pas tout à fait. Par exemple, c'est pas. Voilà.
Il a fixé. C'est logique, sinon, c'est qu'on dit. C'est
we are in a live session.
Yeah.
Okay. Okay, hey, hello everyone. So my name is Daniel Ménard. I come from INSA Rennes. So we are presenting work on reducing the complexity of video encoding. So most of you know that we have a high increase of the internet video traffic due to new services and new video formats. So that's why a new video standard has been proposed. So it's VVC. It has been released in July 2020. And this new standard is able to divide by 2 the bit rate compared to the previous one, which was HEVC. But this efficiency, it's at the expense of a high increase of the complexity of the encoder. So for all intra configurations, the complexity is multiplied by 25 and multiplied by 8 for the random access. So why we have this high increase of complexity? This is due to the RDO process for the encoding. So it can be seen as a combinatorial optimization process. So you have different video parameters and you have to find the optimal parameter for each one. So for example, here you have the tree partitioning. So your block of pixels will be a partition depending on the content. So before there were 2 partitioning in HEVC, you have no split and quad tree, and now you have up to 6 splits. So it increases the search space, and that's why we have increased significantly the complexity. So our purpose is to define a technique based on machine learning in order to select the best split to test. So for that we use a convolutional neural network having at input the coding tree unit in the considered frame and two other CTU, one coming for the previous frame and one coming from the next frame, and each CTU has the best motion vector. So this convolutional neural network based on mobile light is able to provide a vector of probability, and each element of the vector corresponds to the probability of a 4x4 block of pixels. So this is the probability of the boundary of the 4x4 block of pixels. So then we have to define for each coding unit. So you have different size of coding unit. It can go from 100 by 128 by 128 to 4 by 8 size or 8 by 4. So for each CU size, you have a multi-class classifier which will provide the probability of each split, and we will select the highest probability and use them for the encoding process. So here you have the result showing the degradation of the quality. So this is a Bjorndalen bit rate. So when you have a high value, it corresponds to a high degradation. And here you have the time saving. So the best point are those having the best high time saving and low degradation. So you see that we are with our method in blue, we are able to have different trade-off between the time saving and the quality degradation. Okay, thank you.
Thank you very much. Thank you.
Yes, yes. No, no, not the I was not in the main list. That was my promoter. Suddenly something. I'm not sure. Actually, he's going to Spain by fine. Okay. So, no, but maybe grabbing a beer before is an option. Something like this, but I don't know if you organize a session sometime with a good conversation. So I can He always makes me laugh. Each time he takes oh, I got it.
Basically, detect very quickly all of the hats when you start to kind of update it.
there's a problem.
So I need just to put the mic, and it's already on.
Okay, I'll let her.
Thank you. Do I need to start now?
Yeah. Just in my pocket.
Thank you. Sorry. Do I need to start now? Do I need to start? Hello, I'm Danielle from Harvard University in the UK. This poster focused on color image restoration in a no photo count regime using expectation propagation. The problem we're trying to solve is to recover from a grayscale image to a color image. The method we are using is the Bayesian method. In a no photo count regime, the noise follows the Poisson distribution. And in the Bayesian model, we impose a prior distribution on the image gradient using the L1 norm total variation prior. In this problem, the posterior distribution is a high-dimensional posterior distribution that leads to the computational challenging in computing the posterior distribution. And another challenging is the setting of the hyperparameter for the L1 norm TV prior. To overcome these two challenges, we propose two strategies based on expectation propagation. To overcome the first challenge regarding the intractable high-dimensional posterior distribution, expectation propagation proposes the strategy by approximating the posterior distribution using a simple multivariate Gaussian distribution. To overcome the second challenge regarding the optimal setting of hyperparameter, the strategy we propose is to automatically estimate the hyperparameter by computing the expectation with respect to the posterior approximation. Here are the results obtained by our proposed method. It can be seen by using this method, we can get the recovered color image by combining the red, green, and blue channels. And at the same time, a most important thing is that the proposed method provides us the uncertainty quantification for each channel, which is important in decision making. That's our poster. Thank you very much.
And you can take it out. Thank you very much.
Okay, well, perfect. Okay, so
just do one.
Okay, thank you. Hello everyone. So my work is about the image quantization towards data reduction to analyze the robustness for SLAM methods on embedded platform. So SLAM means simultaneous localization and mapping, and I'm more interested in embedded SLAM, which aims at providing real-time performances and minimizing the number of operations performed by advanced perception functions. To do so, we propose to reduce the memory footprint of frame buffers with image quantizations based on three dynamic reduction methods. So first of all, we evaluate SLAM algorithm with the naive method, which is used only for reference purposes, which quantize the input images based on the value of the bin value of the quantization. Then we take the median cut quantization, which is a smart version of the naive methods because it keeps the dynamic of the input images, and the block-wise quantization, which quantizes the images per block of n by n pixels. For example, we take a patch of 4 by 4 pixel, 8 by 8, or 16 by 16 pixels. And we evaluate the SLAM algorithm, 3 SLAM algorithms, because we want to cover a wide range of techniques covered by the SLAM methods. And we evaluated based on the estimated trajectory. So basically, if we have a drone, for example, in my case, I use a data set recorded with a drone. So we take the estimated trajectory of the SLAM methods, and we evaluate it compared to the ground truth provided by the datasets. And for the record, so SLAM algorithms are non-deterministic algorithms. So we need to perform a lot of runs to evaluate the robustness of these methods. For the record, we perform up to 54,000 runs to get the analysis of the robustness of these methods. So to simplify the results that I have, we can see here the two main sequences, the two main challenging sequences of the drone data set, which present lots of speed and lots of variation in terms of light. We can see that we can reduce drastically the data reduction of the input images up to 75% around here, while keeping low localization error. So basically similar to the baseline of 0% of data reduction. And as a main perspective of this work, we want to see the impact of the dynamic reduction in specific parts of the pipeline, because today we only evaluate the accuracy, so the output of the SLAM algorithm, and we want to see exactly where we gain in terms of memory consumption, in terms of computational complexity inside the pipeline. Thank you. Thank you. Thank you very much.
Thank you. Have a good day. Thank you, you too.
Thank you.
Hello, everybody. My name is Mustafa Dia. I come from the University of Champagne-Ardenne, and I present you my work entitled Satellite Image Detection using disjoint information and local dissimilarity maps. Here we present you a classical method depends only on two dissimilarity measures, such as disjoint information and local dissimilarity maps. And the local dissimilarity map is a measure that allows us to quantify and locally the differences, the local differences between two binary and the grayscale images. And the local dissimilarity map, the chance maps, is modeled by the pixel values of the chance maps is modeled by variable distributions. And here we propose our chance detection methods. And if you have two chaotic images, first of all, we partitioning the channel of each image into overlapping block. And after that, we compute the disjoint information between the block at each pixel for each pair of channels. And the values of the disjoint information obtained here is multiplied by the center pixel of the X block. And after doing this pre-processing, we compute the local dissimilarity map of the pair of the three pair of channels. And to have the local dissimilarity map of the color images, satellite images, we compute the average, the mean of the local dissimilarity map of the pair of channels. And here we will have the grayscale chance maps. And to have the binary chance map, we will use a threshold. In our case, we will use the Oates threshold. And here, instead of using the Gaussian distribution to compute the Oates threshold, we will use the variable threshold because our measures, the local dissimilarity map, is modeled by variable distributions. And here, the block size we are choosing here is 15 because if we compute, if we have taken different block size, and we have the size of 15 that give us the best accuracy in these two images taken in the unauthorized satellite chance detection data set. And we have here the ground truth of obtaining in these two images. And we have our approach, the chance maps obtained for our approaches. And we compared our approach with some deep learning unsupervised and supervised methods. And we can see that our approach is lower than the Sahel method in terms of sensitivity. And it is better than the other classical method using the Oates threshold and the PCVR. And in terms of specificity, you have better than the Sahel method and the other classical chance detection method. And we have better than the other state-of-the-art method in terms of accuracy. And to compare for supervised method, we can consider the method proposed by Louis here in this reference too. When the guys use 15 layers, we have better than in terms of sensitivity, and so we have a lower than in terms of specificity, and we have better than in terms of accuracy. And the other method proposed by Dots and the CNN proposed by Dots. The author here he uses the Simon's deployment method, and they gave the best result in terms of sensitivity and specificity compared to our methods. So here the goal of this work is just to propose a classical approach to detect the changes between two satellite images taken in the same place and in different times. And we have here a low complex and simple method and unsupervised, giving the promising results in the chance detection error. Thank you. Est-ce qu'on peut avoir le lien là?
Okay, this round we have just one word to say. Okay? So we take the lead there and did you say another word?
Yeah. Hello everybody, I'm Josef Balón. I'm from University of West Bohemia in Czech Republic, the city Pilsen. And the poster is about detecting of the grid in historical maps. So basically we have the historical map, right? And there are some graphical lines which are like magnitudes and longitudes. They represent the south, north, east, west coordinates. And we are interested in detecting their intersections. Yeah, because these intersections, they can be very useful for georeferencing the image. So it can be overlaid, for example, with modern ones. And how we do it, we basically binarize the image, apply the half-line transform, and after that you can detect the local maxima, which represents the lines. As can be seen here in the first image, you have several lines, also the noisy ones, but according to the angle, because if you presume that you are detecting the grid, you have two possible angles there. You have given angle and its perpendicular angle. So in that case, you basically group these peaks into groups that represents the grid candidate, as could be seen in other images. And also you can like filter the noisy lines because you want to have the distance between the lines the same in all the cases because you have a grid. So finally you obtain the grid candidate, where you can say its angle and also the distance between lines. And it's much more robust than the common approaches that start with detecting the longest or the biggest fragment. Like for example here in the image, you have a long straight road where basically if you will be focusing on detecting the longest fragment or the biggest line, you will probably detect this line or this road. And then it's hard to fit the grid because it's totally different angle. So because of that, probably we also achieve much more or quite good results in terms of F measure or the weighted F measure. Yeah, and that's it. Also, we have the presumption for straight lines, but the lines are like not really straight in the historical image, so we can further refine this intersection because the intersection is rather an estimate of intersection. Because from the previous step we have estimate that is denoted as a green point in the results, but it's not really so accurate to the intersection. So we can utilize the binary estimate from previous step. We can create the template, which is a cross, and it's rotated accordingly to the detected angle from previous step. So we already detected the grid, we know its angle, and now we rotate also our template. Then we utilize the template matching, so we compute some Pearson correlation coefficient matrix. And also we can expect that the error between the points should be from normal distribution. So basically, that's why we also multiply with Gaussian Hill. Yeah, and the result is visualized here in the image, where we basically look for the maximal value, and it gives us like the refinement, like the proper position of the intersection, and it's very precise. Like the majority of the points are closer than 3 pixels on the original maps, which has resolution like 10,000 by 10,000, and that's crucial because for georeferencing purposes, you want to be as precise as possible because 3 pixels can mean like 300 meters in real life, for example. So that's about our approach. Yeah, thank you.
Thank you very much. I hope I wasn't too... No, it was really nice. No, it was really nice. Thank you very much. Thanks.